Imagine for a moment that you are standing in a pitch-black room. You are completely blind. Your job is to identify an object in front of you. Let's say a sculpture. Now, if you just lightly brushed your fingertips against the surface, you might get a sense of the texture, maybe the temperature, but that wouldn't tell you the whole story, would it? To really understand what you're dealing with, you have to grab it. You have to push against it. You have to pull on it to see if it moves, to see if it breaks, to see if it fights back. You have to apply force. For the last century, we have been operating under the assumption that our immune system works like that light fingertip brush. We believed in the lock and key model. It's the dogma we were all taught in medical school. A T cell floats along, bumps into a cancer cell, and if the chemical shape of the receptor fits the antigen, like a key in a lock, click, activation happens. The T cell fires, the cancer dies. It was elegant, it was chemical, and it was intuitive. It was also wrong, or at the very least, it was dramatically incomplete. Welcome to Dr. Evolution's Toolbox, where I share stories of tools we can use to build a better world with biology. The ideas, thoughts, and topics discussed here are my own, and do not reflect the views held by my employer. Today, we are dissecting a discovery that is dismantling that century-old dogma. We are moving from a chemicocentric view of the body to a mechanocentric one. It turns out, your T cells are not just chemical sensors floating in the blood. They are mechanical machines. They are microscopic hands that physically grasp, pull, and twist their targets. And the secret to their activation, the difference between ignoring a tumor and destroying it, lies in a sub-nanometer mechanism hidden deep within the T cell receptor. We are talking about a molecular spring. To understand the gravity of this, we have to look at the paradox that has haunted immunologists for decades. If the lock and key model were the whole truth, then binding affinity should be the only thing that matters. The tighter the bind, the stronger the signal, right? But in the lab, we kept seeing something strange. We could engineer artificial ligands that bound to T cells with incredible strength, superglues essentially. And yet, the T cells would sit there dormant. Conversely, we would see naturally occurring cancer antigens that bound loosely, almost flimsily, yet they triggered a massive, violent immune response. Furthermore, there was a structural problem. The business end of the T cell receptor, the part that touches the outside world, is separated from the signaling machinery, the CD3 complex, inside the cell by the cell membrane. How does a touch on the outside flip a switch on the inside without a physical channel opening up? It was a communication breakdown. We were missing the transmission. The discovery we are analyzing today provides that missing link. It posits that the T cell receptor, or TCR, functions as an anisotropic molecular spring. It is not a static lock. It is a dynamic, tension-based switch. Here is the new reality. When a T cell crawls over a target cell, it doesn't just touch it, it engages. It binds to the antigen, and then the T cell physically retracts. It crawls away, putting the bond under tension. It creates shear stress. We are talking about a force of roughly 10 to 15 piconewtons. Now that sounds infinitesimally small. It's about the weight of a single bacterium, but at the molecular scale, that is a hurricane. This force is the key. The research shows that inside the constant domain of the TCR, specifically in a region called the C-beta-FG loop, there is a structural motif that acts as a sensor. In its resting state, this spring is coiled tight, sequestering the signaling machinery. But when that specific threshold of shear force is applied, when the T cell pulls on the antigen, the spring stretches. It undergoes a conformational extension. Think of it like a safety mechanism on a high-powered weapon. You can put your finger on the trigger, that's the chemical binding, but unless you slide the safety catch back with a specific amount of mechanical force, the weapon will not fire. The T cell must physically deform its own receptor to expose the intracellular signaling tails, the ITAMs, to the kinase enzymes that start the reaction. This is mechanotransduction in its purest form. Now, how do we know this? We aren't guessing. The methodology used to prove this is frankly science fiction coming to life. The researchers utilized a combination of optical tweezers and biomembrane force probes. Imagine a microscopic tractor beam, a focused laser trapping a tiny bead coated with antigen. They lower a single T cell onto this bead, and as the cell pulls, the laser measures the displacement. They could literally feel the T cell pulling. They combine this with steered molecular dynamic simulations using supercomputers to virtually pull on the atomic structure of the protein and single molecule FRET, which uses fluorescent tags to measure distances between protein domains in real time. What they saw was fascinating. They observed a catch bond. Usually, when you pull on a bond, it breaks. That's a slip bond. But a catch bond is like a Chinese finger trap. The harder you pull, the stronger it gets, up to a point. This catch bond allows the T cell to maintain contact long enough to stretch that internal spring. If the antigen is weak or the connection is too flimsy, the bond breaks before the spring can open. The T cell interprets this as noise and moves on. This system acts as a high-pass filter, filtering out accidental collisions and ensuring the T cell only commits to killing when it feels the structural resistance of a genuine target.
So, why does this matter to you, the investor, the clinician, the biotech developer? Because this is the blueprint for the next generation of immunotherapy. Right now, we are seeing a plateau in CAR T-cell therapy. We can cure some liquid tumors, but solid tumors are a nightmare. The big reason is that we are engineering CAR T-cells based on the old lock and key model. We build receptors with massive chemical affinity, thinking stickier is better. But what happens?
Because they bind so tight, they trigger tonic signaling. The spring is constantly jittering, constantly firing low-level signals. The T cells get exhausted before they even see the tumor. They burn out. Or we face antigen escape. The tumor lowers the amount of antigen on its surface, and our chemically driven T cells can't find enough binding sites to trigger a response. By understanding the spring mechanism, we can move into the era of mechanoengineering. We don't just optimize for chemistry, we optimize for physics. We can design TCRs with looser springs, receptors that require less force to trigger, allowing them to activate against tumors with very low antigen density. We can create high-sensitivity T cells that hunt down cancer cells that are currently invisible to our best therapies. Conversely, we can tune the stiffness of the spring to discern the mechanical environment. Tumors are often rigid, fibrotic masses. Healthy tissue is softer. We could potentially engineer T cells that only trigger their spring when they pull against the stiff resistance of a tumor, completely ignoring softer, healthy organs. This would solve the toxicity problems that plague current immunotherapies. We are looking at a future where we screen neoantigens not just for how well they fit, but for how well they hold on under load. We are looking at mechanopharmacology, small molecules designed to lock the spring shut in autoimmune diseases where T cells are too aggressive, or wedge it open in cancer patients where the immune system is sluggish. This is a fundamental shift in how we view biological intelligence. We used to think of cells as bags of chemicals reacting to concentrations. Now we know they are tactile. They feel, they pull, they measure, they make decisions based on physics. As we wrap up, I want you to look at your hand. Clench it into a fist. That mechanical action, that generation of force, is echoed in every single T cell patrolling your body right now. They are crawling through your tissues, pulling on cells, testing their tensile strength, making life or death decisions based on the tension of a molecular spring. We have spent decades mastering the chemistry of life. Now we are beginning to master its mechanics. And that is where the cure lies, not just in the molecule, but in the motion.